Democritus, John Dalton, Joseph John Thomson, Ernest Rutherford, Niels Bohr, and Erwin Schrödinger. These brilliant minds have left an incredible mark on the course of human history, enriching our understanding of the universe and enhancing our everyday experiences. These legendary personalities have shaped our understanding of the atom across 2,400 years. Let's explore the timeline of the atom, unraveling its evolution from ancient ideas to the modern theories of the atomic models. If you want to watch this video in Greek, click here. First and foremost, what is an atomic model? Simply put, it's a theoretical framework that elucidates the structure and behavior of atoms involving fundamental particles to explain their properties and interactions. It all began when Democritus, the ancient Greek philosopher born in Abdera around 460 before Common Era and living until approximately 370 before Common Era, envisioned a world composed of indivisible particles he called atoma about 430 before Common Era. However, some credit Lysippus of Miletus, the teacher of Democritus, as the originator of the atomic theory, while others attribute the concept solely to Democritus. Regardless, their profound ideas set the stage for an exceptional journey through time and scientific discovery. Democritus' philosophical contributions laid the conceptual foundation for the atomic theory that would later resurface in the scientific revolution. While Democritus lacked the empirical evidence we rely on today, his intuitive grasp of the fundamental nature of matter was visionary. He proposed that atoms are eternal, immutable, invisible and unobservable, indivisible and indestructible, uniform, solid, hard, incompressible, and diverse. In Democritus' philosophical framework, atoms weren't solely associated with matter. They also played a role in qualities such as perception and the human soul. For instance, the color white was composed of smooth-surfaced atoms, while soreness was attributed to needle-shaped atoms. The atoms constituting the soul were considered exceptionally fine. His atomic ideas, however, were overshadowed by the influential teachings of other philosophers of his time, notably Plato and Aristotle. Plato, a student of Socrates, emphasized the importance of abstract concepts and forms, viewing the physical world as a reflection of these higher ideals. Aristotle, Plato's student and later the tutor of Alexander the Great, rejected Democritus' atomism. Aristotle proposed a different model, emphasizing the four elements earth, water, air, and fire, and their contributions as the fundamental building blocks of matter. These contrasting philosophical perspectives diverted attention away from Democritus' atomic theories for centuries. As previously mentioned in my video Atom, what it actually is, the term atom originates from the ancient Greek word atomon, signifying indivisible. The etymology of the term reveals its roots combining the Greek prefix a, meaning not, with tom, the augurate of the root of temno, meaning to cut, emphasizing its meaning of uncut or indivisible. It wasn't until the scientific revolution, nearly 2 millennia after Democritus, that his ideas found a renewed interest and paved the way for the development of modern atomic theories. In the early 1800s, John Dalton, an English chemist and physicist, made significant strides in advancing atomic theory. He transformed the ancient Greek atomic philosophy into a structured scientific theory during the period from 1803 to 1808. This period marked a more rigorous and scientific understanding of the atom. Building upon Democritus' concept of indivisible particles, Dalton proposed a more systematic and empirical approach. His key postulates included the idea that elements are composed of indivisible atoms, each with a specific mass and properties. Dalton concluded that atoms are not as diverse as previously believed. Instead, each element is limited to a unique kind of atoms. He introduced the concept that chemical reactions involve the rearrangement of these atoms, but the atoms themselves remain unchanged. Dalton's atomic theory provided a framework that explained the laws of chemical combination, offering a more quantitative and experimentally grounded foundation. He proposed that compounds were composed of different types of atoms in whole number ratios, and chemical reactions involved the rearrangement of these atoms to create new combinations, elucidating certain observations. John Dalton introduced his revolutionary solid sphere or billiard ball model as part of his atomic theory. In this groundbreaking model, Dalton depicted atoms as indivisible, solid spheres akin to billiard balls. His ideas gained widespread acceptance and laid the groundwork for further exploration of atomic structure. However, as scientific exploration progressed, it became evident that Dalton's atoms were not the fundamental indivisible units of matter envisioned by Democritus. This realization marked a pivotal point in the journey through the evolution of atomic models, prompting groundbreaking experiments that would challenge and refine Dalton's postulates and ultimately lead to the recognition of the modern atomic theories we embrace today. Quick mention: this video is part of a playlist on my channel dedicated to the fascinating realm of chemistry, a playlist that will gradually grow with more and more intriguing content over time. Feel free to check it out by clicking on the upper right corner or simply follow the link in the description below. Now back to our scientific journey. It took another 100 years for scientists to acknowledge that the entities Dalton referred to as atoms actually had a more intricate internal composition. In 1897, Thomson discovered the electron through his cathode ray tube experiments. This discovery prompted him to propose a new model for the structure of the atom. Thomson made groundbreaking contributions with his plum pudding model. He envisioned atoms as a positively charged pudding with negatively charged electrons embedded within, resembling plums in a pudding. According to the plum pudding model, electrons were dispersed evenly through the positively charged atomic sphere. This concept provided an alternative to the prevailing view of Dalton's indivisible particles, introducing the idea of subatomic components within the atom. The genuinely indivisible components are currently identified as elementary particles. Check out my video on the standard model of particle physics to understand what everything around us is made of. It's a great complement to our current discussion. Thomson's model was revolutionary in challenging traditional notions and setting the stage for further exploration of atomic structure. However, it was later superseded by more detailed models as scientific understanding advanced. Thomson's contributions remain integral to the fascinating narrative of atomic evolution. In 1904, Japanese physicist Hantaro Nagaoka proposed a unique interpretation of atomic structure known as the Saturnian model. He envisioned electrons revolving in concentric rings around a positively charged nucleus, much like the rings of Saturn. Nagaoka's model provided an interesting alternative to Thomson's plum pudding model. However, this model faced instability issues, especially with electrically charged rings, leading to its abandonment by Nagaoka in 1908.